Okay, welcome back, guys. So we went over determining the end behavior of a polynomial just by looking at the nature of the leading term. And so now what we're going to do is talk about zeros again, zeros of polynomials. Okay. So remember, a zero of any function, not just a polynomial, is just a value for x, such that when you plug it into the function, you get 0. And so geometrically, or graphically, what these mean is it's a value for x such that y is 0. Or in other words, this is a y, or not a y, but an x-intercept. Okay. So if you remember some of that stuff, that an x-intercept is a point where the function crosses the x-axis, but the 0 is the actual value for x, okay, of that point. Or in other words, it's a value, you could call it c, such that if you plug it into the function gives you an output of 0. Alright, so example 4, the first thing we're going to do is we're going to use substitution to determine whether negative 5 is a 0 of the function. Well, if negative 5 is a 0, we should be able to plug it into the function and get an output of 0. Okay? And so that's what we're going to do. You could actually graph it and see if it crosses or touches the x-axis at negative 5. That would be another way of verifying it. But it actually, the directions say to use substitution. So that's what we're going to do. We want to find f of negative 5. So remember, you want to keep that negative in parentheses. -5 plus 15. Let's see. I can do some of this in my head. That'll be negative 125. That'll be positive 25. Whoops. That will be positive 85 with a 15. Well, these first two will make a negative 100. Last two will make a positive 100. And we get 0. Okay, so we can say that negative 5 is a 0 of the function. And graphically, that means that if you were to graph, and we can do this real quick, x cubed plus x squared minus 17x plus 15 Okay, there's the function. Let's inspect it. Let's see. I was looking on the wrong side. Negative 5. In fact, it does cross the x-axis. See that? At negative 5. Okay. So that just confirms that negative 5 is a 0 in that particular function. Okay. Now the next thing that we're going to do is talk about something called the multiplicity of a 0. Now what this refers to is the fact that sometimes a 0 can occur more than once. Okay. So I'm going to give you an example right here. Some functions that have zeros that are repeated. So for example, this function, x minus 1, and the whole thing is cubed. Now this is not written in standard polynomial form. It's actually written in factored form. Okay, but if you were to expand this by multiplying x minus 1 times x minus 1 times x minus 1, you're going to get a cubic equation, or a cubic function. It'll be x cubed plus something x squared plus something x plus your constant. Okay. What I want to point out, though, is that when you find a zero, or one way to do it, and we did this when we were finding the zeros of those quadratic functions, the algebraic way to find a zero is to take your function, okay, whether it's in factored form or not, set it equal to 0 and solve for x. And so if I were to do that, typically that involves factoring. If it's a quadratic function, we could use the quadratic formula, if you recall. But since this one's already factored for us, what we do is we set each of those factors equal to 0. And because I have 3 of them, what am I going to get for my zeros or my solutions? Well, I'm going to get positive 1, but it's going to occur 3 times. Okay? And so in a situation like this, you say that this function has a 0 of 1 with a multiplicity of 3, because it essentially occurs 3 times because you have 3 factors that correspond to that same 0. Now, if we were to graph this function, and we can do this, it's another cubic function. Parentheses that. Oops, let me delete what I previously had in here. Parentheses x minus 1. We're going to cube this. Okay, so I've graphed it. Let's see, where is it? Oh, it's over here. Look where it crosses the x-axis. It crosses at 1. Okay, but in a way, it's kind of like crossing 3 times, because when you factor it, or it's already factored, but when you set those factors to 0, you get the number 1 3 times. Okay, so we say that that 0 has a multiplicity of 3. And the multiplicity of the 0 tells you something. We know that the function, if a certain number is a 0, we know that the function will either cross the x-axis at that value, or it can touch it and turn around. And knowing the multiplicity of that particular 0 tells you what exactly happens. Okay, because sometimes functions, think about our standard x squared function. It only has one 0, and it's 0. The function comes down, touches the origin, and goes back up. Okay, so it doesn't actually cross the x-axis, but it does make contact. All right, well, examples 5 and 6, we're going to get some practice, not only finding the zeros, but also finding and stating their multiplicities. So let's look at example 5. Example 5 here, guys, is another polynomial, but it's not written in standard form, okay, because it hasn't been expanded. It's not a series of terms. However, fortunately for us, it's in factored form, and that's a good thing, because if we're trying to find the zeros, we just take the factors and set them equal to 0. Now, you've got to be careful here, because x to the 5th is a factor, but more specifically, the factor is just x. It just occurs 5 times. So if I take that one factor and set it equal to 0, it's already solved. One of my zeros is the number 0 itself. But because it has an exponent of 5, that means there's 5 factors of x. And if I were to set all 5 factors of x to 0, I would get 5 zeros. Okay? And so consequently, we can say that the 0 has a multiplicity of 5. Okay? Similar to this previous example, the 0 was 1, and it had a multiplicity of 3 because that factor occurred 3 times. Now my next factor in this function is x plus 2. And if I set that equal to 0 and solve it for x, I get x is equal to negative 2. So negative 2 is another 0. But because I have two of these factors, then that 0 would occur twice. So we say that it has a multiplicity of 2. And then similarly with the last one. However, the last factor only occurs once. And so when I solve for x, the 0 that I find, which is 7, only has a multiplicity of 1. Okay? So when you have your polynomial in factored form, the multiplicity of each 0 corresponds to the exponent of the particular factor from which you derived the 0. Okay. All right. Now let's go, and you could graph this one in Desmos as well, or in your calculator. You'll see the function. Now it may not cross at every one of these zeros, 0, -2, and 7, but the function will at least touch, okay, if it doesn't cross. And we're going to look at here in a minute how to distinguish whether it crosses or just simply touches without actually having to graph it. All right, let's look at example 6. The directions are the same. Find the zeros of the polynomial function and state the multiplicity of each. However, this function is in standard form. It's not been factored for us. Okay? And so if we want to find the zeros by setting the function equal to 0 and solving for x, we're going to have to factor. All right, so this will give us an opportunity to kind of review factoring. I'm going to zoom in here. All right, so I'm going to rewrite it. I'm going to set it equal to 0. And then I'm noticing that on the left-hand side, now it's not quadratic, okay? However, I notice that it has exactly 4 terms. That's an indication to me that it could be possible to factor it by grouping. And so that's what I'm going to try. I'm going to group up the first 2 terms. You always want to put a plus sign. And if that third term is negative, that negative follows the number. Okay. So I've got them grouped up. Now what I'm going to do is take out the greatest common factor from each of these groups. Well, in my first 2 terms, they each have 2 x's. So I can factor out an x to the second. And so when I do that, that'll just drop the powers of those x's by 2. So x cubed will just become x, and then x squared will just become a 1. You may be saying, well, why does it become anything? Well, when you take out the x squared, you're basically undoing the distributive property. So if you wanted to check this, you would think about, well, if I distribute this x squared back through here, I still need to get a negative x squared. So how will that occur? Well, I need this to be a -1 for that to happen. Now, in my second group, I have 2 terms. What do they have in common? Well, they definitely have a 4 in common, but I'm not going to take out a 4. I'm going to take out a -4, and you'll see why. Okay. So to see what's left, you can go back and divide by -4. And so -20 divided by -4 is 5. You'll have the x left. And then here, 4 divided by -4 is -1. And so now what we have, hopefully you notice this, is that these factors, these binomial factors, match. And that's what we have to have happen when we're doing this factor by grouping. Because then what we do is we look and we say, what do these 2 terms have in common? Well, they both have that binomial, 5x minus 1, in common. And so we take that out, And when we do so, we just have the x squared and the minus 4 left over. Okay. And so this right here is the factorization of my polynomial. So now that it's factored, I'll set it equal to 0. Or more specifically, I'll set each of those factors equal to 0. Okay. And I'm going to solve them each for x. This first one here, I'm going to need to add 1 to both sides of the equation. Now divide both sides by 5, and I'm going to get x is equal to 1/5. That is one of your zeros. Now determining the multiplicity hinges upon how many times did that factor occur. Well, it was a binomial factor, but it just occurred once because it doesn't have an exponent out here. Okay, and so therefore the 0, 1/5, has a multiplicity of 1. Now we move to our next factor. When we set it equal to 0, this is actually a quadratic equation. It's got an x squared. It is in standard form because it's set equal to 0, so you could solve this using the quadratic formula if you want. Or you can solve it directly for x. That's what I'm going to do, because it's missing the middle term. So I'm going to add 4 to both sides. I'll get x squared is equal to 4. But to convert an x squared into just x, I must take the square root of both sides. And when I do this, you've got to remember that when you take the square root of the other side, you get 2 roots. You get both a positive and a negative. And so the square root of x squared is just x. The square root of 4 is 2, but we get positive and negative 2. In other words, we get 2 zeros. We get positive and we get negative. But what are their multiplicities? Well, most students will say 2. And the reason they say that is because there's an exponent of 2 in this factor. But the multiplicity of these zeros is dictated by the number of factors that we have. Okay, not what's in the factor. The factor itself is x squared minus 4, but it only occurs once. Okay, and so whatever zeros I get out of this factor, their multiplicities are just 1. Okay, so 2 has a multiplicity of 1, negative 2 has a multiplicity of 1, and then 1/5 has a multiplicity of 1. And a third degree or cubic polynomial can have no more than 3 zeros. That's the maximum number. Okay? The maximum number of zeros is dictated by the degree of the polynomial. All right. Well, the last thing we're going to do is what I mentioned earlier. So if we know the zeros and the multiplicities, we know that the function will have some sort of contact with the x-axis at that particular value. But how do we determine whether the function touches or whether it just, well, I did not just gesticulate that correctly. How do we know whether it touches, maybe goes up to, touches, turns around, versus does it actually cross the x-axis? Well, that hinges upon the multiplicity of the zero, whether it's an even or an odd number. And that's what this tells you here in the notes. K represents the number of times that the factor occurs. Okay, if x minus c, where c is just some number, c would be the 0. K tells us the multiplicity because k tells us the number of times that that factor occurs. And so these two bullets tell us that if k, or the multiplicity, is odd, then the graph will cross the x-axis at that 0. But if k, or if the multiplicity of the 0 is an even number, then the graph is tangent to the x-axis at that value. What tangent means is it touches it, okay? So it comes up to, touches, and then goes back down, or comes down to, touches, and then goes back up, okay? Alright, so let's look at a couple more examples. It says determine whether the function is tangent to, you can just think about touches, or crosses the x-axis at this point. Okay. Well, this point is an x-intercept. The function is going to be intercepting somehow the x-axis at 9, whenever x is 9. Well, which of these factors does 9 correspond to? Well, you would get a 0 of 9 from this factor right here. Okay. In fact, I'll show you. You just take that factor, set it equal to 0, add 9 to both sides, and you get x equals 9. But what's the multiplicity of that 0? Well, that hinges upon that exponent, 4. That means that that 0, 9 would occur 4 times. And 4 is an even number, okay? So the 0, 9, which corresponds to this point right here, this x-intercept, has a multiplicity that's even. And so if the multiplicity is even, the graph touches or is tangent to the x-axis at that particular point, okay? The book uses this terminology, tangent to the x-axis at the point 9, 0. And I'm going to show you this because we're going to graph it. Now again, this is a polynomial, but it's not in standard form. It's in factored form. It's x minus 9 to the 4th times x plus 3 to the 9th. Oops. The 4th times x plus 3 to the 9th. Okay, there's my function. Now let's look over here at 9. Look what's happening. Now you may be thinking, well, that's kind of weird, but the more we zoom in, we can discern there's a gap in there, and that the function is actually coming down, touching the x-axis at 9, or at that point, that x-intercept, and then going back up. So the function is indeed tangent to the x-axis at that point, 9, 0. Okay. The other 0 would be -3. That would come from this factor. Okay. And the multiplicity would be 9, which is an odd number. So we should see the function cross the x-axis at -3. So let's zoom out and see if that's actually the case. And come over here to -3, and in fact it does, doesn't it? It's kind of hard to see. We have to just keep zooming in because it looks like it's parallel, but it is actually crossing right here at -3. It's just that for these values of x, the function is so close to the x-axis it's indiscernible. But you know, if you could just zoom in and zoom in and zoom in, you know, you'd eventually see maybe a separation there. But anyway, see, it's pretty evident it has to be crossing here, right? Because how can it go from one side of the x-axis to the other side if it's not crossing? Alright, well, let's tackle one more if you don't mind. Number 8, just like the last one. It says determine whether the function is tangent to or crosses the x-axis at this point. -7, 0. So the 0 itself is -7. It would have to come from this factor, okay, and that exponent or multiplicity is 3. I'm just going to explicitly show you. So if you were to take that factor, set it equal to 0, you'd subtract 7 from both sides, and you get that the 0 is negative 7, but it has a multiplicity of 3 because this factor occurred 3 times. Now 3 is an odd number, which means the function will cross the x-axis at that particular point, negative 7, 0. Okay, and we'll graph this one as well so I can show you. X minus 5 to the 4th times x plus 7 to the 3rd. Oops, I need to make that an exponent. 3rd, there we go. So where's negative 7? It's over here, and look, the polynomial is in fact crossing at negative 7 because the 0, negative 7 has odd multiplicity. Now let's look at the other 0, which would be positive 5 because it comes from this factor. Its multiplicity is 4, which is even, and we see that the graph is tangent to the x-axis at that point. Okay, so hopefully this is starting to make sense. The idea here, guys, is these were, these theorems, or these properties were developed long before graphing calculators were around. And so, mathematicians or engineers, whoever, they needed a way to be able to analyze the behavior of a function. They didn't have graphing calculators to just graph it and see actually what was happening. So they proved a lot of these properties, and these were very instrumental. Okay. So anyway, well, that pretty much concludes 8.1. We're going to continue talking about zeros and their multiplicities, and also the connection between the fact that if you know a factor of a polynomial, that factor corresponds to a 0 and vice versa. So anyway, I'll see you in 8.2.